Well, we didn't finish 12, did we?
We did finish 12. I'm going to go through 12 one more time because it's essential to understanding 13. So, why does this keep getting bumped down? All right. So, before we get back into this guy, okay. All right. Remember, we have perpendicular bisector theorem, and it says that if you have this, right, a perpendicular bisector, then that means that from these guys right here, right, this point will be equidistant. So you get this, right? That's perpendicular bisector theorem. Cool? Now the converse of that is just the opposite, right? So if I'm given this, a point that's equidistant from these two, right? Then I know by the converse, that this point must lie on this guy's perpendicular bisector. So if I were to draw it, it must go through that point. That's the converse, right? We good?
Yeah.
Okay. All right. Now, also recall, I am allowed to assume for any triangle that there exists a midpoint somewhere on a side, right? Does that make sense? Every side's going to have a midpoint. Yeah, this isn't going to fly. All right, so I can say let that be the midpoint, right? And I can connect dots if I want. Totally valid. So vertex to midpoint, I can create a median whenever I want. Right? It's going to be somewhere. I'm allowed to assume that. I'm also allowed to assume an orthogonal at any time, vertex to 90, right? Otherwise known as an orthogonal, right? Totally valid, right? There's going to be one somewhere. Even in an obtuse triangle where things are really weird, right? There's going to be an orthogonal here. I'm just going to have to extend this side out, right? Now, we typically, when we work with orthogonals, deal with these types of triangles just because the proof will be the same. It'll just be a lot prettier to look at, right? So I can assume vertex to 90. That's valid. I can also assume for any triangle that this is a midpoint. And, well, this is a bad example. Let me go to this little crazier triangle. That's a midpoint. And I can go 90 from there, right? Totally valid. So midpoint to 90 is totally valid. All right, so vertex to midpoint, vertex to 90. Or these two put together, right? Totally valid. What I cannot assume is that I've got a line that goes from the midpoint to 90 and also goes to here, right? I can't do that because not all triangles are going to have that property, right? Not all perpendicular bisectors go straight up to the opposite vertex, right? Only in isosceles or equilateral triangles does that really happen. So we cannot assume this. So when I do vertex and it's 90 and it goes to the midpoint, that's way too much assuming, right? We have to prove one of those things. Yeah.
So if it's an isosceles triangle, you can assume it goes straight up?
Yes. You know why? Because of this. Right? Does that make sense? Right? Yeah, it will. And we've proven that. It's perpendicular bisector theorem. And if it was equilateral, I mean, right, same thing, right? For an isosceles, this guy would work, right? If it was equilateral, I could draw all of them, and they'd actually all go to the opposite vertex. In fact, when you have an equilateral triangle, guys, when all sides are equal, the center of that triangle will be the incenter, it'll be the orthocenter, it'll be the circumcenter, and it'll be the medicenter. All of the centers line up at one spot on an equilateral triangle. Cool. All right. So I can assume these three, but I can't assume all at once, right? Cool. So when I'm doing the perpendicular bisector proof that they're concurrent, I need to create some perpendicular bisectors. Totally valid, right? I can assume midpoint and I can assume 90 degrees up. I just can't connect it to the opposite vertex. That's not guaranteed, right? So what I do first is I say, well, let there be a midpoint here, right? Every side has a midpoint, right? No matter what side length I give you, can you cut it in half? Yeah, totally cool. So let this exist. And let this be the perpendicular bisector, right? Ooh, that almost goes right through A. I'm going to tilt it just a little bit so it doesn't. Because we cannot assume that. So I can assume that. Totally fine, right? I can say let this be the midpoint of this side. We'll call it point F. And I can say let this be the perpendicular bisector of side AC, right? And they're going to connect at one point, right? They both go through the triangle. So at some point they're going to intersect, right? Unless these are parallel. And that's just not going to happen, right? We would need these sides to be the same side for them to go parallel, right? That just doesn't happen in a triangle. So we say that they're going to intersect at some point. Let's call it point K. So when I write this, like over here, right? How do I write that? I say let there be, because I'm creating stuff. Let there be DKE, perpendicular bisector of side BDC. We cool with that?
Why is that different than what we did on the same?
So I just did it all in once. I'm giving you less steps. I might have also put it down there, yeah. I'm doing the sides and leaving this available because I think it'll be easier to see it if you don't, okay? Again, you can pick two, right? 2 of the 3, yeah.
I already have this written down.
I know. Yep. Going over it again. And we're live. All right, so also we're going to do this one, right? I'm going to call that FKG. So we're going to let FKG be the perpendicular bisector of AFC. Right? Something like that. Right? Cool. That covers all our bases. We show the intersection point, right? They both intersect at K, et cetera, right? So now I'm going to prove that if I drew the last perpendicular bisector, it would also go through K, right? These two, they intersect at K, some random point, right? I'm going to prove that that random point is actually where this last one's going to intersect too, right? So first thing is I'm going to say, look, by perpendicular bisector theorem, K is going to be equidistant to B and C. So let me say it again. K is on this perpendicular bisector, right? So it's going to be equidistant to this guy's endpoints, right? That's perpendicular bisector theorem. So I'm going to draw a line from K to B. Boop. And I'm going to draw a line from C to K. And I'm going to say those distances are the same. Has to be. That's perpendicular bisector theorem. Now, by the same logic, isn't K also on this perpendicular bisector? Right? So by perpendicular bisector theorem, K is going to be equidistant to C and A, the endpoints of this segment, right? So I'm going to draw that in. And this makes sense, because what do the perpendicular bisectors intersect to form? What center do they form? Circumcenter. Circum means go around, right? So what are these actually? What are these actually? Radii of the circle that goes around it, right? That makes sense. So of course they're all equal. I've proven that they're equal, which is why the circle exists, right? We have a point going from the same distance in all 3 directions, right? We're going to have a circle, right? So now that I know that, that's my perpendicular bisector theorem. My perpendicular bisector theorem, I proved that, not EK, AK is congruent to BK was congruent to CK. Right? Cool. Well, here's the thing. AB, if I were to draw its perpendicular bisector, it would have to go through K. And the reason is that K is equidistant from A and B. Remember, we said if it's equidistant, then it must be on the perpendicular bisector, right? Is K equidistant from A and B? Yeah. So by perpendicular bisector theorem converse, it must go through K. So I'm going to write that. K is on the perpendicular bisector of what? What segment? What side of the triangle is that perpendicular bisector coming out of? The one I'm talking about. The one I have to add. AB, right? This side. Right?
Yeah.
Are you following me? It's okay, it's okay. Seeing it's the hard part, right? Which is why I highly suggest you watch. That's not a good sign. All right, so AB. That's the last perpendicular bisector I got to draw, right? So I'm proving that K must be on AB's perpendicular bisector. That's all. Well, if K is on AB's perpendicular bisector, and it's on BC's perpendicular bisector, and it's on AC's perpendicular bisector, it's on all the perpendicular bisectors, isn't it? So I win. I write that. Therefore, the perpendicular bisectors of triangle ABC are concurrent. I'm not going to write that, but that's what I'd write, and I'd be done.
You already answered that.
It's on AB. It's on DE. It's on FG. So we're good. I'm sorry, let me say that again. It's on AB, it's on BC, and it's on AC's, right? So there we go. We're done. Not hard to write, hard to see. But much like an optical illusion that you have to go in real close and then pull back, right? And then once you see it, of course, right? Of course I see the ship, right? Once you see it, you're good. But it's 90% of the battle. So if you don't see it, of course you feel lost, right? Looking at this right now, if I were just to be like, hey, beginning of class, hey, this is true, copy that down. You would have no idea what it meant. But if you watch in real time, it makes a difference. Which is why video is such a good idea. Yeah.
Do you have the quiz reviews printed out yet?
I do.
Awesome.
Reviews or retakes?
For the reviews?
I have all the reviews for all the quizzes. Oh, for this? No, I don't. I'm going to give you those tomorrow. Sorry. Sorry, I got to make them. I'm behind. I spent 12 hours here yesterday, and then I spent 2 extra ones after work working on stuff, and my opinion was 14 hours a day of work is enough. So I stopped there. Because I got to make sure I'm good to go for the show, right? Yeah.
Are you staying late today?
Yes, I will. Yep. I stayed late yesterday. For you and Marissa.
We have dance.
I know. How late was I supposed to stay? I stayed until 6:15. Were they supposed to stay later?
I think we get done at 5:30, then we had to go straight to dance.
Oh, gotcha. Are you doing that again today?
Yeah, because I have practice.
Hold on. So you get done at 5:30, and then you do go to dance.
I have a dance class. at
Okay, so
6.
when do I need to be here? That's what I need to know.
I don't have the dance class today.
You don't have it today? Okay,
No.
gotcha. Okay, because yesterday Marissa was like, oh, could we do both days? I'm like, of course. When? She said 5 o'clock. 6:15, right? Okay, but it was fine. Not mad, I just, want to know. All right, so let's move on to the next one. Page 13. I've made my triangle thicker. I'm going to go over the concept again. Okay? Dang she thick.
But which one was it that we were doing at the end of class yesterday that had like
13.
3 million?
It's not as bad as you think. It's not.
You didn't write anything down.
Oh yeah.
Stay with me. Okay? That was the end of class yesterday. You were shot by then, right? Here we go. Here's what I'm going to do. Before we get into this, let me reestablish this sort of lemma, right? We learned a while ago
Yeah.
that if you have a triangle, all sides have a midpoint, right? Somewhere. So let's just let this be the midpoint here. Let's call that the midpoint. Let's call this the midpoint. Right? And we know if we connect these sides up, we get mid-segments of the triangle. That's what these guys are called. They're a special segment. We just haven't talked about them very much. And they create what's called a medial triangle. This guy in the middle, right? So, we proved a while ago that if we have this situation, then this triangle here is similar to the big triangle, right? Right?
Wait, which triangle?
This triangle, similar to this triangle.
Yeah.
Okay, we did that a while ago. You don't need to remember that, but we did that a while ago. And we proved that that meant that this length right here is half the bottom. Okay? And we proved that, therefore, this must be half of this bottom, right? And that this must be half of this. You remember that?
What's that called?
So can we just do that all in one step now?
We're going to. I'm going to explain. Now, we also learned that not only are these two sides connected by half and double, right? But they're also parallel. And same thing for every other opposite side. These sides will be parallel. And these sides will be parallel. Okay? That's always true. So we call this medial triangle theorem that allows us to get all these parallels and all these congruent sides. Boom, done. You get all that. Now here's the amazing part. Every triangle you draw, no matter how weird, is going to have a medial triangle inside of it, right? Because every triangle is going to have midpoints, right? And can I connect the dots? Sure. There's the medial triangle. And if it's a medial triangle, this side is half of this side. So it's just one, right? And this side will be half of this side. And this side will be half of this side. And not only that, they'll be parallel, right? These two parallel, these two parallel, these two parallel. Every triangle has a medial triangle. What we're going to do today is we're going to do the opposite of that. We're going to have a triangle. And I'm going to say that's the medial triangle of some other triangle. That's the hidden triangle. This right here. We're going to do it in reverse. I'm going to say, let there be a line that's parallel to this. I'm going to draw it over here. Let there be a line that's parallel to this. I'm going to draw it over here.
What's that called? Ortho?
Let there be a line that's parallel to this. And do you see I've made the bigger triangle? Right? And that was the hidden triangle the whole time. So these two are parallel. And not only that, but this is half of that, right? Yeah?
Since their sides like go together, do their angles go together?
Mm-hmm. All these triangles are congruent.
Oh, congruent?
Yeah, they will be congruent, actually. Yeah. Like exact same triangles. All of these are the exact same triangle.
But they're not, they don't have the same.
Check it out. These sides are matching, right?
Yes.
Okay. So the big triangle is not congruent to the little guys. That's what I'm saying. The little guys are all congruent. We good with that?
Oh, yeah.
We good with that? Okay, cool. All right, cool. Gotcha. All right. So, same thing with this, right? This will be half of this side, and this will be half of this side. Now, if my original triangle was called triangle ABC, right, the OG triangle, the hidden guy, right? Aren't A, B, and C the midpoints of the big triangle? They are, aren't they? Right? So if I were to draw a line straight up, what kind of line did I just draw? A perpendicular bisector, right? Perpendicular bisector of the big triangle, right? And we just proved perpendicular bisectors always intersect at one point, right? So if I were to do that for all the sides, they would all intersect at one point. Okay, I'll get there. Better question. These two are parallel, right? The two green lines? They're parallel. And the line I just drew goes through them. That's a transversal. Two parallel lines and a transversal. Inside the parallels, opposite side of the transversal. Alternate interior angles. If that's 90, that's 90. Do you see it? Two parallel lines. The line I drew is a transversal. I said let it be 90. Right? I can always do that, right? So that's 90. Right? Now check it out. This is the vertex, right, of my original triangle. I'm going to highlight this. Just this much. Not further, but just this much. What kind of line is this? What kind of special segment is that? It's an orthogonal. Vertex to 90. It's an orthogonal. So if I take the perpendicular bisector of the big triangle, a piece of that is the orthogonal of the small triangle. We're going to do it again. This is a midpoint, right? So if I draw straight up from there, that's the perpendicular bisector of the big triangle, right? You with me there? These are parallel. That's a transversal. That must be 90 by alternate interior angles. Now, again, the perpendicular bisectors intersect here, right? If I highlight this much of the perpendicular bisector, what kind of line is that in the small triangle? What is it? It's an orthogonal, right? It's vertex to 90. And they intersect here. I'm going to do it one more time. Purple side. I'm going to draw a line straight up, and I'm going to cheat a little bit because I didn't draw my things very well. So that's perpendicular bisector of the big triangle, right? Of this side.
Yeah. Wait, yeah.
Now, if I highlight this much of it, two parallels, transversal, alternate interior angles, right? So what is that highlighted portion? It's a what of the small triangle? What kind of segment is that?
Perpendicular bisector.
Nope, it doesn't bisect. We don't know that.
Cancel out.
Orthogonal. It's not diagonal, it's orthogonal. Right?
Yeah.
And notice, my perpendicular bisectors all intersect at a point. Not surprising, we proved that earlier, right? The perpendicular bisectors of the big triangle all intersect here.
Yeah.
And since the pieces of the perpendicular bisectors are orthogonals, right? They also intersect there. So my orthogonals are concurrent. Guys, the perpendicular bisectors of the big triangle intersect in the same spot as the orthogonals of the small triangle. In other words, the circumcenter of the big triangle is the same as the orthocenter of the small triangle. Circumcenter goes with perpendicular bisectors, right? Orthocenter goes with orthogonals. They're one and the same. The perpendicular bisectors of the big triangle hit the same spot as the orthogonals do in the small triangle. So all I'm doing is proving that this big triangle, that the perpendicular bisectors are concurrent. And we just did that, right? And then by extension, the orthogonals of this guy are concurrent. Okay? I'm going to do it again. Let's do it on this page. I'm going to show you a couple times. The writing is actually not crazy bad. It's just a lot of letters, okay? So, I'm going to make a side. Let's use different colors. Red, yellow, and blue. Let's do that. Ellie, darker one? Okay. So, let's make a line that's perpendicular to this guy. Ooh, that was a good choice. That was a good choice. Let's brighten this up just a little bit. There we go. I'm going to make a line perpendicular to BC. So, I'm going to get out my ruler. That's right, taking out Saddam. So, okay, I'm going to say it's parallel. I'm not going to tell you the letters yet. I'll do that in a second, okay? I'm going to make a line that's perpendicular to this guy. Or, sorry, not perpendicular, parallel, right? So parallel to this, about there. Cool. It's parallel, so says me. You cool with that? Right. And then lastly, let there be, let's not use red, let's use a different color. You want to use orange, or we want to use like green?
Like the weirdest color you have.
Orange? Ellie.
Cool.
That one.
This one.
Sorry.
It's okay.
I'm sorry.
I should have asked Landry. Right?
Yeah. Well, I'm sorry.
That's right. And Landry is an artist herself. Ew. All right. I like that. I like that a lot. I like that laugh. All right. So I just drew 3 lines that are parallel, right? Totally red. I can do that, right? That's valid, right? Where they intersect, I'm going to call D, E, and F. You cool with that?
Cool.
So I'm going to create a parallel line, DCF, parallel to AB, right? So let's write that, or at least I will, okay? Let, and I'm going to say, yeah, let there be line, DCF, parallel to AB, right? Cool with that? Right. Let there be DAE, parallel to CB, or BC. Let there also be this guy, FBE, parallel to AC. Okay, that's all I did. You cool with that? Now, we know by medial triangle theorem converse. Remember, medial triangle theorem is when if you have a big triangle and you make the medial triangle, then all the sides half and double and parallel, right? The converse is if you have the medial triangle and you draw one around it, then these will be twice as big as this and parallel, right? So on and so forth, right? So by medial triangle theorem, converse. I know that this, right? Okay, I'm going to write that. I'm going to say that AC is congruent to BF is congruent to BE. Cool with that? Right. I know that these guys are congruent. So it's a pain in the ass to write because it's alphabet soup, but like the logic is not hard, right? So I'm going to say BC, AD, medial triangle theorem converse, AE. And lastly, these guys, AB, congruent to CD, congruent to CF.
Wait, so the medial theorem converse tells
Medial triangle theorem converse, there's a triangle in
tells
there.
us that for example, the blue line tells us that A is like the midpoint of that.
Essentially, yeah, that's what it tells us. It tells us that this is going to be twice as big as this guy.
Okay.
And this will be twice as big as this guy. And this will be twice as big as this guy. Right? Cool. Now, what Danny pointed out is brilliant. Doesn't this mean by definition that A, B, and C are midpoints of my big triangle? Yeah, right? Now, I don't need to state that.
I thought that's
We already said that, right? We're good.
I thought that's what we started with.
We just drew parallel lines. And then we got congruent segments, which implies that A, B, and C are midpoints, right?
Oh, that was the upper problem.
So, yeah, if I were to draw a perpendicular line to this line, right? I'm going to draw it like that. Then that would be the perpendicular bisector of DCF. So I'm going to call that line CE, let's call it G, or CG. Because I haven't done that yet.
Why wouldn't you call
And I'm going to call this a point. Actually, let's call this G. And instead of using H, because H is just I sideways, depending on how we turn the diagram, it can be confusing, right? I'm going to skip straight to J. So we're going to say, let CGJ be the perpendicular bisector of DCF. So I'm going to write that over here so you can see it. So again, still let. We're just creating stuff, right? So let CGJ be the perpendicular bisector of DCF. Now, I'm going to do that for all these, but everybody knows my next step, right? After I get all these down. This right here is 90. These are parallel. This is a transversal. So by alternate interior angles, this, right? We cool with that? So I'm gonna keep drawing these guys and doing that, okay? So I'm just gonna say let this guy be the perpendicular bisector. So let's call that, we use J, let's call this K. Ooh, perfect. And I'll let that be L, okay? And I'll have this be M. Okay? Just using letters, okay? I need that one because that's where they intersect, right? And then just a point that it goes into on the opposite side, and then where it keeps going to. I really don't need M and J. You could stop at L and G if you wanted to. It's totally fine, okay? So I'm going to say let BKLM, or BLM, let's do that. Doesn't matter. Be the perpendicular bisector. What side is this the perpendicular bisector of? Side what? What side is this the perpendicular bisector of? FBE, yeah. We want the B in there so we know that's where they intersect, right? Cool. We're going to say let K be the point of intersection at some point, but it's fine. I'm going to do the same thing here. So I'm going to do alternate interior, right? Cool with that? I would do this as you go, right? All right, so next, I'm going to draw the perpendicular bisector from here. So let A, we use M, let's call this N, and let's have this be, I'm going to skip O for obvious reasons. Go straight to P. So we're going to say let ANP be the perpendicular bisector of, what side is this the perpendicular bisector of? It's the blue side, right? it perpendicularly bisects the blue side. What's the blue side? DAE. Okay. Cool with that? I just drew those in. This was a perpendicular bisector, so I do alternate interior. And I get that this is also 90, right? So now I'm going to do my alternate interior angles theorem. By alternate interior angles theorem, angle MAK is congruent to angle A and B.
Is that AI?
Is everybody cool with that? This angle here is the same as this angle here,
Yeah.
right? That's all I'm saying. These two are going to go together, and these two are going to go together. So that's angle K. Let's do, yeah, KCF. And that's going to go with AGK. Again, alphabet soup. Alphabet soup. I know, KFC almost, right? And then EBK is going to go with CLK, something like that.
I actually put that as KFC. Jeez.
All right. Now we're almost done. Okay? The only theorem I even used in all of this is alternate interior angles. Everything else was just let there be, right? A lot of construction. So, and thank you, you're welcome for not making you have to do this with a compass, and yeah, you're welcome. Okay, so let K, we're going to say let K be the intersection point. K, or let's do this. Let CKJ, AKN, I'm just highlighting that's where they intersect, and BKL exist. Right? And what are CKJ? I'm going to use a different color to highlight. Let's use minty green. CKJ, or CKG, I should use G. G, make that a G. I had a GIF moment, sorry. It's GIF. What is CKG? Oh, doesn't bisect this side, we don't know that. It's an orthogonal, right? And what is AKN? AKN. An orthogonal. And what is BKL? And they all have K in it. So they're all concurrent. Therefore, the orthogonals of triangle ABC are concurrent. I could have had you say, by definition, these are orthogonals, right? But I'm just gonna, who cares?
So like, I feel like I could draw the triangle, but writing it out.
This is where I normally, like, if I were doing this on a whiteboard, like my old schools, I'd just, like, take the markers and leave the room for 5 seconds. Like, mic drop, but, like, also, like, you know, spike football. Yeah. Let me zoom in and see if I can get all of it in the picture. No. Okay. You zoom in. Yeah. Technology. And then my old classroom had like these like splatters of paint, which was really like the expo markers exploding, right? That you couldn't get out of the floor. They loved me there. I go, pow! But you guys don't know that what that's a reference to. It's a reference to Bob Dole and his attempt to win the Democratic nomination in the 90s. He got really excited after winning one primary, and he's like, "We're going to Iowa, we're going to Texas, we're going to Iowa!" And he did that, and then he lost everything after that. But that's,
So I could draw the triangle diagram, but I can't read.
Bob Dole. Bob Dole didn't take no crap. Bob Dole. Bob Dole.
Wait, was that the guy that always had the weird
Can
hat?
you?
I think, yeah.
Yeah.
What?
Start zooming on the pink stuff.
The pink stuff? Yeah. It's red.
It's not red.
Idiots.
Angle.
I'm going to do it again, but I want to give you a break, okay? So here's what I'm going to do for you. I'm going to grab something out of the copy. I'll be back. Some of you guys wanted more homework. Somebody asked for that.
Also, I figured out just take one of these little notches off, I can have normal size laces again. Also, these shoelaces are apparently wax. Because they just use them.
Are you digesting? Are you taking a break?
Hang on 1 second.
The proof itself is not hard. Seeing it's the hard thing and knowing what to do, right? Here's what you need to do. Create parallels. Then you've got a medial triangle, right? And all of that gives you, right? All the congruent stuff. Draw some perpendicular bisectors. And then give them a lot of letters, right? Tell me where they intersect. And you win. After alternate interior angles. Sorry, I'll break that down again. Draw the parallels, right? We'll zoom out. Draw the parallels. Give them letters. Label your medial triangle, right? Double, half, double, half, double, half, etc., right? Draw perpendicular bisectors. Tell me where they all intersect. By alternate interior angles theorem, these guys go together, these angles go together, these angles go together. You win. And you feel like a god.
How many points would I get on the test if I drew that triangle and the diagram right, but didn't write anything?
Hey Matt, do you know that concurrent
Guess not much.
adjectives two or more certain sentences to be certain at the same time?
Concurrent means to be done at the same time in the colloquial sense, right? So two lines done at the same time at the same point, right? Turns out time and space are interchangeable if you think about it. So, how do we feel? I'm going to do it again if we have time. If not, I'll do it first thing for the review, okay? But it's basically perpendicular bisector theorems, right? Or perpendicular bisectors, right? Get either orthogonals. Again, the amazing thing here is that the perpendicular bisectors create a circumcenter for the big triangle. And that circumcenter will be the same thing as the orthocenter for the small triangle.
I listened to that.
That's okay. That's the deal. Gentlemen over here, your days are numbered. I will be splitting you up. Much to the chagrin of many of these people, and to their dismay. Because if I split you up, it means I have to move some of them around. It's going to piss them off.
No.
Wait,
So
why?
congratulations, you have successfully pissed more people off in this class.
Why? Why are we getting moved?
All right.
No. No, I can't even
Sorry.
How did these fit on in the first?
Oh, we can go back to my old third and he was writing sit behind me. God. I was in
And we sat all over there. It was like 3 people and then everybody else was over here.
Wait, did your first semester have this? Yeah, mine
I had it in a while. All right, so quiz version 2, 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 quiz version 2. Here it is.
Oh,
That's
yeah.
No way.
Wait, what's this?
Mr. Beck, who requested hold?
First hour.
Watching it happen, I
Who's
think
in your first hour? You didn't come to that with
Right, which is why it takes some practice. So when you study for this, right, I would practice doing it with this example and see where you get stuck. Break it down into ideas. Don't memorize the letters, right? Because the letters you make up. The ideas are draw your parallels, right? Then you've got a medial triangle. What does that mean? Right? You get congruent sides. Then draw your perpendiculars. Tell me where they intersect.
These in my next hour.
How come we're split up?
Alternate interior. And you're done.
We haven't done anything either.
Nobody else does this.
Let me say it again. For those of you that are freaking out about how many things are here and all this writing. First we drew the parallels. That's this. Then we had a medial triangle, which means we get all these congruent sides, right? Then we drew perpendicular bisectors, right? That's like the crux of the theorem, right? We're going to draw the perpendicular bisectors for the big guy. And then we do alternate interior angles theorem. Tell me where they intersect, and you win.
So you just say that a bunch of stuff exists. And
Don't worry. Yeah, exactly, right. All of this exists.
That's made great enough.
Alternate interior means those are all 90, right? And then tell me where they intersect and you win.
So just make things exist, use that, tell them where they intersect, and that's.
Yeah. Is it a lot of writing? Oh yeah. And you create your own letters, right? But don't think of it like that. Okay? Think of it as ideas. You can copy down letters as you go. That is not hard. You don't need to study that crap. Okay? There are a couple ideas here. Draw parallels. Get a medial triangle, which means congruent sides, right? Draw perpendiculars, perpendicular bisectors, right? Alternate interior angles, where they intersect, done.
This could be a painful degree.
As painful as it is for you guys. Imagine the kid that's trying to BS this, right? And I have to read through all that and be like, is that sort of right?
Is that kind of?
Yeah.
Well,
Shout out to Evan Scott, who is now a god at geometry, by the way. He just retook quiz 2, and he probably got the best grade out of anybody ever. That quiz 2 retake is brutal. All right, so Evan, well done. The man is a god. All right, if we didn't know that already. He was a legend before. All right, so. These are easy.
No, they're not.
Yeah, they are. They are.
Are you sure?
What must G be? What center must G be?
Medius, medius. Orthomedial.
Are these orthogonals?
Yes.
No, because they don't go from the vertex to 90, right? They don't.
No.
But this goes from vertex to something, right? What kind of segment is that?
Bisector.
Angle bisector. So what center must this be?
No,
The in-center. There's a little circle inside here. There's a little circle inside here. And what are the radii? 5. So what's x? 5. Now how do we find y? May I remind you that radii always intersect at 90 degrees to the opposite side. How are we going to find y?
oh, because, so then F intersects at 90 degrees, and then it's kind of like, wait.
This is a right triangle.
Yeah, and then.
So we can use Pythag. 5 squared plus 12 squared equals y squared. 5, 12, 13 is a special right triangle. So if you did 5 squared, that's 25. 12 squared is 144. You add them together, you get 169. What's the root of 169? 13. So y is 13. It's a right angle. I have 169 memorized as a root because it's funny. Most people have 12, right? 144. And they stop it before 13. I'm like, but why? Don't you know? All right. G. G is the circumcenter. Okay. So if G is the circumcenter, what kind of line segments must these be? If it's the circumcenter, what lines make the circumcenter? Perpendicular bisectors. So if that's perpendicular, that must be the perpendicular bisector, right? These both go through G. So if it's perpendicular and a bisector, it bisects this side. So what's x? You just need to know your crap, right? You just need to know your crap. There's no BSing this. If you know it, easy. And if you don't, oh my God. Oh my God. Now, if this is 3, how are we going to figure out what y is? It's kind of a trick question. How do you know it's 8? Because that's also a perpendicular bisector, right? So 4 and 4, right? Y is 8.
How is it a bisector?
It has to be because it goes through G and G is the circumcenter, right? The only perpendiculars that can go through G would be perpendicular bisectors, right? Okay? No proof. Now, if this is 8, what's this whole side?
6.
Now, if G's the circumcenter, and the circumcenter's where? It's on the side of the triangle, right? When is the circumcenter on the side of a triangle? What kind of triangle? Acute, right, or obtuse? Right. So this must be a right triangle. So how can we figure out Z? Pythag. What's 6 squared plus 8 squared? 36 plus 64. 100. And what's root of 10? Or root of 100? Guys, it's just a 3, 6, or a 3, 4, 5 right triangle, but doubled. That's it. G is the medicenter. What does that mean about these lines? What lines must those be? Medians, right? And medians always have a 2-to-1 ratio. So if that's 8, this is 4. If that's 6, this is 3. If that's 5, this is double 10. Now, aren't medians vertex to midpoint? Right? So that means this is 5 and that's 5. And this is 3 and that's 3. So what's y?
We should make our I can't speak English.
Hotel?
Our whole test.
Yeah, if you do that, like.
Yep, work on it for homework. We have similar triangles on the backside.
No, do Friday.
Do Friday, but I would highly encourage you to do it for tomorrow because there's going to be stuff like this on the quiz. And I would like you to review this so we don't have to review it tomorrow because it's super easy if you know what you're doing. Later.
Look at geometry problems.
Yep. And then these are vertical. Oh, but will they be similar? Can we prove that? No, we can't. I don't think we can figure out x. Or at least we could. Maybe we could when I could. When I did it earlier. I think I wanted that to be another 8, and then this would be isosceles. But that's okay. That's okay. That's okay. Don't figure out x for number 3.
Well. Matt probably in after school today to take the test and understand what the hell is going on.